Industrial Engineering and Computer Science, and founding director of the Center for Social Services Engineering at the University of Toronto. Within the University of Toronto School of City, he's the director of the Urban Research Center and past associate director of the School of Cities in India. Prof pioneered the field of constraint-directed scheduling and the development of ontologies for modeling enterprises. He's currently investigating the application of ontologies to the representation and utilization of city knowledge, including social services, shelters, transportation, and water and sanitation. He's actively involved in the development of international standards for city data based on his urban ontology research, including ISO and IEC 21972 upper level ontology for smart city indicators, and ISO 5087 series of cities data modeling standards. Within the social service sector, as part of the Common Approach project, he led the development of the Common Impact Data Standards, impact modeling and reporting. Dr. Force is also an entrepreneur, having co-founded Carnegie Group Inc. in 1984. Carnegie, sorry. That's a cool thing. Carnegie, sorry. A software company that specializes in artificial intelligence-based systems, and co-founded and was CEO of Novator Systems, pioneer in e-retail software and services. Dr. Force is a fellow of Association for the Advancement of Artificial Intelligence, Institute for Electrical and Electronic Engineering, and the Engineering Institute of Canada. Dr. Force has published over 250 papers. Thanks for coming, guys. Thanks for coming.
Thank you, and again, I apologize. I totally screwed up by putting it at 12 noon. I must have seen something about 12 noon in one of the emails. I don't know which one, but the latest was 11 a.m. Okay, I'm going to talk about data, and I'm going to attempt to motivate you as to why the work that we're doing with respect to data is important to transportation research and other types of research. A lot of people, especially engineers, don't give too much thought to data itself, the innate characteristics of data, beyond needing data to do the research, beyond having to figure out where to get the data to do the research. We are interested in the nature of data itself, and that is, I rarely find that degree of interest in a lot of domains. I attribute it to it's easy to talk about data, but it's more difficult to understand deeply what data means. I attribute it to people who are more interested in the problem they're trying to solve as opposed to the nature of the data itself. And there's nothing wrong with that, okay? That's great. But what I'm going to try and do is convey to you what I think are interesting aspects of data that tend to be left out, tend to be ignored when solving problems. So, what I have to say is relevant to transportation, but it's relevant beyond transportation. And so why don't I just dive in and try and create the context for why the nature of data is so important. So we live in a world where everybody wants smart cities. I think we're at the point now where smart city as a phrase is now the past. We'll just talk about cities in general. But obviously, today when we talk about cities, we talk about cities that are efficient, sustainable, resilient, citizen-centric. I can throw in all the appropriate buzzwords that you hear about cities today. And that in order to achieve that, we need to be making better decisions. And of course, if all of you are civil engineers, the nature of the tools that you used up until about 5 years ago were sort of standard mathematics that you learn in your undergraduate programs. Now, if you haven't taken a course in machine learning, AI, statistics, etc., then you're not going to get too far in your research today. And so there's a variety of techniques that are appropriate to making decision makings within city better, but it requires the capability to coordinate planning and operations across city divisions, external stakeholders. Okay, this is something that you may not necessarily consider if you're just narrowly focused on transportation, in that there's a lot that goes on in the city separate from transportation, and there's a lot that goes on in the city that requires the integration, coordination across the different departments and divisions of the city. And so you may not think that social services cares about transportation, but social services does care about transportation. Because in a world where we want to provide services to citizens, where we locate those services in various parts of the city, the first problem that people who need social services have is figuring out a way to get from point A to point B in a reasonable amount of time and reasonable cost. I mean, quite frankly, social services give bus fare to people who come in just because they can't afford to make their way across the city. And all that has changed over the last decade in that where social services are located, which used to be mostly in the downtown core, and spread out across buildings in the downtown core, then began to spread out across the city because the demographics of where people, low income, et cetera, are located in the city has spread into the suburbs as the gentrification of the core of the city has pushed people out who can't afford to live in a core. So suddenly people, to get services, have to be traveling long distances to various parts of the city. And as we know today, if you have a car and you want to get from one end of the city to another, forget it. So transportation is not only an issue for transportation departments, it's an issue for all the other departments that exist within the city, because they rely on transportation in various ways, and when they're making decisions, they need to coordinate in some way with the transportation decisions are also. But all of this coordination, planning, operations, et cetera, both internal to city and external stakeholders, ultimately relies upon the sourcing and integrating of data from across the city. So everybody relies upon data, okay? And the reality is, most of the data that we rely on to make our decisions, planning decisions, operational decisions, et cetera, is crap, okay? Most of it is garbage, and then we build these models and make decisions, all based upon this very low quality, sparse data, et cetera, and think we're doing the right thing. So it's almost like the pollsters in a way. You know how in the U.S. when they poll people at the elections, they always get it wrong, right? But they're extrapolating from the data that they have. Okay. Now, Transportation Research Institute here has been conducting a survey every 5 years of transportation needs. There are models of how households grow over time, et cetera, but how often do we stop to ask whether 1 day's worth of travel every 5 years is truly indicative of what the travel needs are? Okay? It's no different, and it's not, and transportation isn't unique in that sense. In the whole world of the homeless and social services, they make decisions based upon a 1 day count of homeless, on 1 day count of homeless once every whatever number of years, okay? And to think that 1 day's worth is going to really be indicative of what's going on there is problematic. Now things are getting better, right? I mean, we have cell phones, so we actually have movement data for a statistically significant portion of the population. Just think if our Presto card actually was used to tap off in addition to tap on, we may even have real trip data, at least for public transport use. So things are getting better and better. So for some reason we can't get it right, at least at the Metrolinx level. But anyway, we still have problems with data. Now, here's the problem that I want to focus on. It's that what's in red there. If in order to build better planning systems, in order to build better decision-making, real-time decision-making systems, we need to be able to utilize data that comes in from multiple sources. Okay, we need to be able to integrate that data. And that's not easy. To make that a little clearer, it's not easy because we don't know if the data from one source is semantically the same or different than from other sources. Okay? And the example that you see here is not from transportation, but from Parks and Recreation, water and sewage. In the information systems of each of those departments, they may each represent something called a plant. The interpretation of plant in water and sewage will be some physical building that produces drinkable water or processes sewage so that sewage water so that it can be put into Lake Ontario. Whereas Parks and Recreation use the same word for something different, something green and leafy. So the integration of data from across the city poses a huge semantic problem because the meaning of the attributes and the meanings of the values may not be uniform. That is, they may not be the same thing. They may not be using the same attributes. They may not be using the same values. And even if they are, they may not be semantically interpreted in the same way. They have different meanings. So, semantic interoperability, which is the core of what we're trying to achieve in achieving integration of data from multiple sources, is not about syntax. We don't care if it's XML or if it's a spreadsheet or JSON or whatever the case may be. That's just syntax. What we care about is what the meaning is of those attributes, meaning of those values, etc. And are they consistent? Are they the same? Well, in the Urban Data Research Center, we have a service which is called the Canadian Urban Data Catalog. And it can be reached at data.urbandatacenter.ca. And it is a catalog of urban data sets. Currently, there's approximately 43,000 data sets that are in that catalog. So if you're looking for data, we're hoping to achieve a one-stop shopping place. That is, if you're looking for data sets, start there, and then you can move up. And the reason why the Urban Data Catalog is created is because data sets are spread all across Canada. Some of them are open, some of them are closed, some of them are web services. The problem of knowing what data is where and who to contact is a problem. So I went to the Urban Data Catalog at data.urbandatacenter.ca and I typed in the word transportation. I don't know how many data sets came up. There was probably 3,000 or more data sets that are related to transportation. And what I started to do was pull the data model for each of those data sets. And so the left one is from a data set on transportation activity indicators from Transport Canada. I don't know how well you can see it. Marine to the rest of the world, rail to the rest of the world, road to the rest of the world, air from the rest of the world, marine from the rest of the world, international freight total 20-foot equivalent units. Transportation expenditures also from Transport Canada has 3 attributes: transport expenditures, population per capita transport expenditures. Wellbeing Toronto has a transportation data set which talks about pedestrian and other collisions, road kilometers, road volume, traffic collisions, TTC overcrowded routes, TTC stops. Land information, Ontario, transport points. I have no idea what those attributes mean. And then I went over to Natural Resources Canada for mode of transportation to work. And I'm just putting up the address XML there, which you probably can't see that easily. The point I'm trying to make is there's nothing that's shared from a data modeling perspective, attributes, values, etc., Well, some values may be, so like the names of provinces are shared. Names of cities may be shared. That's about it. All the data models are different. So if you're going to take data from multiple sources, then the onus is on you to figure out what the data, what the attributes mean, and what the values mean, and then figure a way to map the data onto each other. So just this very simple exploration of transportation data sets and the data models they use demonstrates the lack of standardization, the lack of uniformity, the lack of semantic interoperability, just off the first 4 or 5 that I picked out. So what's the solution? What I'm going to say here today is that the solution is an ontology, and an ontology answers the questions: what are the core concepts and properties that span the domain's data, and to what extent can we generalize them in a useful way? And what are the key distinctions? Can we formally define necessary and sufficient conditions for something to be an example of a concept? Okay, so what does all this mean? It means somehow we need to seek a general data model, general in the sense that can be applied across all these different data sets, that can be applied across all these different, not only transportation domains, but a variety of other domains, so that you can then map the data from multiple data sets into that common ontology. And what distinguishes a common ontology from just sitting down and saying, I'm going to create a data model, okay? And everybody here is probably taking a database course somewhere along the way as an undergrad. Everybody here has learned about relational databases, and if you haven't learned about relational databases, you know what a spreadsheet is, okay? So basically we're talking about tables. Everybody here has learned about that, and everybody here thinks that they can be a good data modeler because they created a spreadsheet or a table that has columns and rows to put their data into. What we do in ontologies is we say, if we want something that can be generally used across a number of different applications, not necessarily just in transportation, but across many other applications, what would be the general versions of the concepts that we want to be able to capture in our ontology? What are the characteristics or properties or attributes of those concepts? And just as importantly, which properties are used to distinguish one concept from another? So if I'm talking about vehicles, what properties distinguish a truck from a car, a bus from a minivan? Okay, and that's what that second piece is. What are the key distinctions? Can we formally define necessary and sufficient conditions for something to be a bus, or to be an Uber car, or to be whatever? And so we seek out a general understanding of what the things are, the concepts that need to be represented, and what the key properties are about them, and the properties that are used to distinguish one concept or category of concepts from another, from another, from another. So that's ontology building in a nutshell. Now, the technology we use for creating ontologies is formal logic. So when we describe a concept, we don't just say, here are the properties. We then create a formal definition of that concept using the properties. So, let's take a look at what an ontology is. Already talked about that. So an ontology has 3 parts to it. The lowest level of an ontology is what is today referred to as a knowledge graph. Who here has heard of what a knowledge graph is? So, one person knows what a knowledge graph is. It's just a fancy name for a network. What distinguishes a knowledge graph from just any type of network representation is the identification of nodes and properties. So we have a, quote, ontology that says, here are the standard concepts represented as nodes, here are the standard properties represented as links, and if I want to represent a particular concept like a bus 38, particular bus, then I make it an instance of, I instantiate the bus concept with the information about bus 38. So the knowledge graph contains both the ontology and the instantiation of the ontology, the specification of things using that ontology. So the properties are defined by the ontology, so there's a standard set of properties, and the types of nodes are defined by the ontology. But the actual domain, the actual application where you have specific buses, specific people, specific roads, etc., use those nodes and links to then construct the specific information. So let's talk about knowledge graphs in the context of transportation planning. So we all know what transportation planning, because that's one of the major areas of the Transportation Research Institute. It's been that way for a long time. We want to predict what transportation demand is going to be over a multi-decade horizon. There's a lot of things that we have to do in terms of predicting how the population changes over time, what modes of transportation they're going to use. And so I'm going to create an ontology that's going to be used in transportation planning. Then I need to be able to represent things like residents, households, members of households, the transportation network, vehicles, and it goes on and on and on. Okay? But those are the types of concepts, and members would be, let's say, a property. The next level is definitions and constraints. So to have a knowledge graph, to have that network, doesn't take us all the way through to an ontology. The next step is to be able to define our concepts. Sometimes I use the word class. I still haven't replaced those concepts. To create definitions of concepts and any constraints on their interpretation. So for example, what's the definition of a Toronto resident? Okay. Turns out Toronto resident definition is that they reside in owned property or owned or operated business in Toronto, and a household is composed of at least one person who resides at the same address. So basically a household is multiple people residing at the same address. So those are definitions. And what value is there for having a definition? Well, if some data set somewhere has the concept household, we have the concept household. If we have a formal definition of what a household is, we can compare it to somebody else's definition of household and determine whether they mean the same thing. And if you want, you can automate that process because it's all done in formal language. But having that level of precision becomes important because if you just say, in my database, I have this class or table called household, okay? Nobody knows what that means, except you, maybe. So having explicit logical definition becomes very important. Then the third level is what we refer to as microtheories. And what they are axioms or rules that are used to make inferences with. So in the transportation planning world, for each year above the age of 14, a member of a household will leave with some probability P of H. And obviously that's used for predicting 2, 3, 4 decades out into the future what the composition of a household is going to be. And that wouldn't be the only rule. We have to have a rule that deals with divorces, that deals with people who age, that people who die, with births, all that type of stuff has to all be there if we want to develop a microtheory of how households change over time. Okay, let's take a little closer look at this. How do we represent an ontology, a city resident? Example, if we want to provide free transportation for senior residents, how do you recognize, how do we recognize that they are a resident of the city of Toronto? Well, we have to have a definition. So with these ontological descriptions, we can verify that people who request the service is a resident. Or if somebody gives you a database, you can use it to determine whether somebody is a resident, that they satisfy the definition. Or you can infer characteristics of residents, such as they live in the city of Toronto. So, here are different examples of city resident depending upon the city that you're looking at. And the reason why I'm showing this is because you can't have a single definition of city resident. This will become important a bit later. Each city has their own, or country has their own definition of residency within the city. And so we could talk about a resident in general. What would be the most general conceptualization of what a resident is? That they be a person, maybe. That they reside within the country of that city. That may be as general as you can get. Or they reside in the city itself. That may be as general as you get, but it doesn't capture all the different things that go on here. We're going to place particular attention. We're going to look at the Toronto one. You are identified as a resident if you reside in, own property, or own or operate a business in Toronto. That's a resident. So the question now is, how do we represent that in a knowledge graph? So, that's the English, that's the knowledge graph. What you see in purple are what we refer to as concepts, word classes. So we'll use the word concept. So that's a general notion of a resident. A Toronto resident is a subclass of resident. And a Toronto resident has a number of properties. Owns property in Toronto. And Toronto here is an instance of the city. I don't show that. They reside in Toronto, operates a business. Business has an address, which has a property in city, Toronto. Okay, so if we just stayed at the knowledge graph level, we can get our hands on what the properties are and what the concepts are. But what we're missing is the actual definition. Okay? We don't know from what we see here whether they have to own property in Toronto and reside in Toronto and operate a business in Toronto, because we're missing the logical connectors. And so the actual representation, the actual definition, going to the next level, beyond the knowledge graph, now has the statement, Toronto resident is a subclass of resident and resides in Toronto or owns property in Toronto or operates a business, and that business has an address, and that address is in the city of Toronto. So that is a paraphrasing of the logical representation. The logical representation looks like this in what's called description logic, but you have a formal language by which you can now specify the explicit definition of what it means to be a resident of Toronto. Once you have that, then you get all the other capabilities of automatically classifying an individual based upon whether they satisfy the definition, whether an individual who's classified as being a resident is a resident or not. So you accrue a number of benefits that allow you to do inferential reasoning about people in their relationship to being a resident in the city. Taking us to the microtheory level, remember microtheories for each year above the age of 14, a member of the household will leave with probability. We see the same concepts of classes that appeared in the knowledge graph. Person didn't appear. Household didn't appear, actually. So person X, household Y, a member of XY, and age greater than 14 has probability of leaving ZPL. And so using other concepts, other properties that weren't in the previous slide, we can now define explicitly what the inference rule is for somebody leaving a household. So what does this leave us with? As I said earlier, you can't come up, there is not a general definition of city resident that tells you much, because cities, countries have very different definitions of what a city resident is. And so what the ontology allows you to do is it gives you a toolkit, and that toolkit is composed of concepts or classes, and properties. And so you can construct a definition of a Toronto resident, or a Beijing resident, or a Mumbai resident, using these concepts and these properties. And you can use logic to provide the definitions. So that's what it allows you to do. Let's skip over this. And I'm going to go straight into the iCity transportation and planning ontologies. Any questions before we move on?
So like you create the ontology manually, like you take the definition and manually like you
Traditionally, it's manual,
okay.
but there is a process that we go through.
Okay.
And the process begins with use cases, the ontology. It then goes to what are called competency questions, that is, the questions that the ontology has to have the ability to answer if it has the data. And then it goes to the definition of the concepts and properties, and then the formal definitions, etc. A lot of people leave off the formal definitions. Yeah. We call those light ontologies. Any other questions? Okay. So, I'm going to quickly go through some of the work we did. I'm not sure when we started, 2015, 2016, 2017, something like that. It was part of the iCity 1 project, which was funded by the Ontario Research Foundation. The PIs were Eric Miller, I forget who the co-PI, I'm a co-investigator, but Eric and someone else were the PIs for the project. So I was a member of that project, and you all know about ILU and GTA model and all that type of stuff, right? So this is an older diagram of the GTA model version 4. I don't know what it looks like any longer, but you're all aware of what Port Howe is place of work. Port Pos, I guess, is place of school. Anyway, so there's all these modules there that generate trips for one day. And the problem that we were looking at is if you want all of these different modules to share data, what would that shared representation be? What would that ontology be? And so that's what we started working on in the project. And so that meant we had to examine each of these modules within the GTN model to understand what data they were manipulating, what data they consumed, what data they produced, what data they shared with other modules, et cetera, to try and come up with an ontology that generalizes the representation of that data across the modules. The result of that was an ontology that had a number of different, what we refer to as concept patterns. So for example, location would give us the concepts and properties related to geospatial locations. Time would give us a concept and properties relevant to representing time intervals, time durations, the relationship of time, one time to another being before or after or during or whatever. Units of measure allows to represent any type of unit of measure, people per day, whatever unit of measure you can imagine. Change is all about how do we represent how concepts change over time. So if you have a bus, how do you represent the fact that at time t1 the bus has the following information, time t2 it has the following information, time t3 has the following information, and have that all related to each other so that you can just query the knowledge graph and pull out, say at this particular time, how many people are on this bus, as opposed to having some data someplace that's just a log of number of people on a bus and having to keep going out to these logs and searching it. The change representation allows it to be explicit within the graph itself. Activities, how do you represent activities? What resources do activities use? What has to be true of the world in order for an activity to be performed? How does the world change after the activity is completed? And mereology is just a fancy name for part ofs. How do we represent something as part of something else? Whether an engine is part of the vehicle or whatever. On top of that, we have a representation of sensors. And let me just say, some of these things like location and time and sensors and units of measure are built using other ontologies that have been created by other people across the world. So when we create an ontology, we don't start from scratch every time. We start by finding other ontologies that actually satisfy our requirements, our competency question. Sensors is W3C, SSN. Household, person, organization, contact all come out of the work that we had done previously. Buildings and land use build on other ontologies, vocabularies. And then the transportation network, transit vehicles, travel costs, trips, and parking all utilize other bias to meet our needs. So to represent a road pattern, there's the most basic concept of an arc. Arcs have start and end nodes, and in this domain they have posted speeds, they may have tolls, they support various modes of transportation, and arcs are the most general way of describing something that allows you to get from one point to another. And a road like Bloor Street would have multiple arcs. Arcs representing the bike lanes, arcs representing the sidewalks, arcs representing the roadway itself, etc. And arcs representing the subway. So any particular road would be a bundle of these arcs to represent all these different modes, etc. And the geospatial information would be part of that in terms of, you can see road segment has a location, which has a geometry. So all that is embedded there. People are members of households, they occupy a dwelling unit, units in a building, buildings have locations, we have trips performed by a person associated with some activity like going to school. The trip has a start location and end location. It accesses an arc, which means it's accessing some means of getting from point A to point B. And it goes on what's in there. And we have trip patterns that provide information about the route, what arcs it operates on, what vehicles are being taken, etc., what the schedule is. And there's more and more and more and more. There's absolutely no way I can go into detail about this. So if you want to find out more about the iCity transportation ontology, you just have to go to ontology.eil, it's on utoronto.ca, and on that page you can click down to the ontology we created, and it gives you all the files covering activities, buildings, change, geometry, households, land use, monetary values. OM is our measurement, is the measurement ontology that we use. Organization structure, parking, public transit, spatial locations, transportation system, trips, travel costs, etc., etc. So after we did that work, we asked ourselves, what would be the best way of getting this work out into the public? Well, of course we published papers on it, but we decided to engage with the international standards organizations. And so we engaged with ISO-IC, JTC1, W11, Smart Cities. Let me decode the acronyms for you. ISO is the International Standards Organization, which you may have heard of. IEC is the International Electrotechnical Committee, which is another international standards organization. Joint Technical Committee 1 brings those two standards organizations into a joint standard group. And WG11 is a working group within that Joint Technical Committee 1 that focuses on ICT for smart cities, information and communication technologies. So what we did was we proposed to Working Group 11, on smart cities, the creation of a series of city data standards. And that proposal for city data standards was informed by work that we did in our group. TOVE is a set of ontologies for enterprises. So it's an enterprise ontology. As you can see there, it covers activities and organization structure and behavior, costing, resources, skills and competency of people, products, et cetera, et cetera. GCIO is the Global City Indicator Ontology, is another project that we had been pursuing, which created ontologies for representing and measuring the performance of cities across a variety of themes: education, water and sewage, public safety, transportation, et cetera, et cetera. And the Global City Indicator Ontology is everything in the light blue, and it builds upon the ontologies that we created before. So the stuff in the green is the TOVE ontologies, and that's then used for the GCIO ontologies. And all of that then fed into the iCity ontology, as you can see by the color coding. The blue is from GCIO, the green is from TOVE, et cetera. So all that fed into what we proposed to do with Working Group 11 on smart cities. And that resulted in the creation of the 5087 series of city data standards. So the point here is we were not just creating a standard for transportation, we're creating a standard for city data in general to allow cities to be able to standardize how they represent their data. Now, cities have a major problem because of their organization structure. They're composed of silos, and each of the silos, whether it be transportation or water, sanitation, parks and recreation, et cetera, have created their own information systems, created their own data models, and it's very difficult for them to share information. So the intent here is to allow for semantic interoperability across the cities and their external stakeholders, and not just be focused on transportation. So the structure of the framework of the 5087 series of city data standards begins with a low-level foundation ontology for representing concepts such as time, location, and activity. So this is really general, generic across any type of application. The next level is what we call the city level, and this represents data that is commonly found across a lot of the different departments and services that a city provides. So this could be things like households or services or residents. So that type of data is read and updated by multiple services within the city and outside of it. And then the third level is what we call the service level, which represents data that is in essence owned by one service or department in the city, but shared with other departments. So the owner can only do the updating of it, and the others can just read it. So for example, transportation planning is a good one because the transportation department owns what the transportation network is and publishes it to, the transit network is, and publishes it to other parts of the city. But nobody else can change it, only the transportation department can change it. And 5087-4 is for public health emergencies. Next one is housing. After that, water and sanitation, etc. So this gives you an idea of the concepts that are each level. So 587-1, 2023. The 2023 means that it's been published as a global standard. So it's now available to anybody who wants to get hold of it. 507-2, 2024 was published earlier this year, is the city level set of standards for city data dealing with buildings, infrastructure, land use bylaws, city people, contracts, organization, residents, sensors, services. And wherever you see some text underneath it, like W3 SSN, is that this particular set of concepts and properties are based upon the W3 sensor network standard. And down here, it's based upon W3C organization, vocabulary. Over here in location, we use OGCs, GeoSparkle. Anyway, so we build on existing standards where they exist and they're appropriate for what we want to do. And then at the next level, transportation, this standard is being worked on at this time. So there's a group of people from both WG11, the Working Group 11 on Smart Cities, and people from ISO TC204, which is the Intelligent Transportation Systems Technical Committee. And they're the ones that do all sorts of standards with respect to transportation, whether it be telematics or anything else. So we work jointly with them on it. And then we're also working on public standard for public health, city public health data, medical activities, resources, public health events, et cetera, et cetera. So the bottom line is that we've taken all of this and we've now put it, packaged it as a set of standards so that it can be widely available to others for adoption. And then finally, what we've been doing is building what we refer to as the City Digital Twin. And I'll just run, let's see what my time is. Okay, I'll run through this very quickly. The City Digital Twin, you should probably know about it. Everybody hear the word digital twin? Don't know the phrase digital twin. Okay, some do, some don't. Okay. So city digital twins are computational representation of the city or a portion thereof for the purpose of design, planning, analysis, and/or operation. So it can be used for many different things. The representation may span the goal structure across these activities, resources, people, behavior, information constraints of the city. But what is actually represented is determined by the application for which the digital twin is going to be used. Okay? And it can be both descriptive and definitional, spanning what is and what should be. So it's not only today, here's what things are, or a year ago, but also what could be in the future for using for planning purposes. From a design perspective, people use digital twins to determine what the impact is going to be if you make changes to the city. Within the realm of transportation, there's been a lot of work on city digital twins focused on transportation and primarily focused on 3D views of buildings and where the roads are. And if you're doing transportation planning, it gives you a nice little visualization of traffic moving, which are fun to see, but usually irrelevant for what you want to do because you want to analyze the data. You don't want to see a car moving down a road. That doesn't really mean that much. So you need to distinguish the visualization, which are fun, from what data is actually, what it's actually doing and what data it's using, etc. From an operations perspective, it could be used to represent what is planned, what might happen, what has happened, and it could be used to provide information and knowledge necessary to support the operations of the city. Now, there's one thing that you need to understand is a city digital twin is in essence a surrogate, a substitute for the thing itself that is often used to determine the consequences of the changes or actions that you may perform, so that you're reasoning about the city rather than taking action in it. Because cities are larger, complex things, cities often do things without truly understanding what the impact of their action is going to be. Because they have no way of, in essence, simulating it or et cetera. So a city digital twin is meant to help in the ability to predict. But as you know, with either the GTA model and all that, it's all about predicting what's going to be. Okay? And question then becomes, are our models good enough to do actual predictions? And that brings us to the question, how close is surrogate to the real thing? What attributes of the original does it capture and make explicit, and which does it omit? Perfect fidelity is in general impossible, both in practice and in principle. It's impossible in principle because anything other than the thing itself is necessarily different from the thing. All representations are inaccurate. They inevitably contain simplifying assumptions. The level of fidelity is determined by whether the representation is fit for purpose. This is a real interesting question for all the work that we do. Okay, we go get data, we create a model, we make predictions. How valid are these predictions? Is the model fit for purpose? Does it have the right level of fidelity? And I often ask myself when I see the work done in the Institute about predicting what travel times are going to be if you take down the QEW or things like that, whether they really do match up with reality. Let's see. So we've been building our city digital twin for some time, and the goal is to create what we refer to as a general city digital twin, which means it's independent of the city. And it's independent of the city for the following reasons. So the way our city digital twin works is we can take data from a large number of sources. And we saw earlier 5 data models from transportation data sets, and they were all different, no overlap. So when we take data from StatsCan on demographics from a census, they have their representations of things. When we take data about the physical infrastructure, where the streets and buildings are, they have their definition of what's there. Social infrastructure, where the schools are, what social services are available, where are they available, et cetera. When we take data like crime, all these have different representations, okay? Different data models. So we're back to the semantic interoperability problem. And so what we do is we create a pipeline that allows us to map the data coming from the variety of sources that are out there and map them into the data standards that we have been working on for a number of years, so that we have a single representation. So the challenge is to do that mapping into that one standard for representing all the data. And once we do that mapping, we can then link all the data together, because when they refer to the same thing, we can link them directly using properties. So we can link our census data to the infrastructure data, et cetera, et cetera. And if we can link all that together, which we do in our city digital twin, then we can build on top of it a variety of algorithms that determine whether a community is complete, that determine what the indicators of the city are as defined by global standards, SDGs, things of that nature. We can determine, we can support the analysis of mixed-use development, housing potential, et cetera. And we have a interface that then allows us to access all of that, whether it be map-based or indicators, pie charts, et cetera, or natural language question answering. So the city digital twin already has an interface. And what's interesting about this is when you start using it, you first have to select the city, and then once you select the city, you then select what are referred to as administrative areas. An administrative area is dependent upon the city. So when I said this has to be general, independent of cities, if I'm dealing with a city in Quebec, their administrative areas, wards, census areas, neighborhoods, et cetera, they don't have the same administrative areas. If I'm dealing with a city in Europe, they won't have the same administrative areas. And so there's nothing in the interface It knows nothing about what the administrative areas are for Toronto or Montreal or wherever in the world, because all that's represented in the knowledge graph. So the definition of what the administrative areas are, of what an administrative area is in the knowledge graph for a particular city. And the definition of what the administrative areas are for a particular city is in the knowledge graph. So the interface knows nothing about the city. It just pulls data from the knowledge graph because it's all interconnected. It's already there. And so you just have to select what you want. Pick the city. It gives you a list of administrative area types. Choose the type. I want a neighborhood. Then it pulls out what the neighborhoods are of that city. For Toronto, let's say the annex. Then you can, in this case, we're looking at indicators. You then select whatever indicators are available for it, which is also in the knowledge graph, and go ahead and show you visually on a map where the different neighborhoods are. It can show you the values of the indicators. If you have multiple neighborhoods, it can combine all that in bar graphs and visualizations like that. It can bring in the census data, because all that's interlinked within the knowledge graph. So if you're looking at a particular neighborhood and you want census information, the algorithms automatically map the census data into the neighborhood, because the neighborhood could be composed of multiple census areas or overlap multiple census areas. So it does the algorithm to pull the data for the neighborhood to get census related, population related information. You can point and click and dive into closer, more deeper information about the neighborhood. And you can also analyze the data in the knowledge graph from a complete community's point of view to understand things like, all this is changing, but with respect to parks, what it's showing here is the park access score. So in complete communities, you usually say it's 15-minute neighborhood or 15-minute community. So what that score is that residences within that neighborhood, which in this case is South Parkdale, are within a 15-minute walk of a park. So it's, what is it, 98% are within a 15-minute walk of a park in Parkdale. So you can do that type of analysis, etc. So I'm at the end. So what I've tried to convince you of is data is real messy. And data is real messy because everybody creates their own data models. They are documented poorly. They are not using any formal method of defining what the data model is. Everything's stuck in English or French or whatever. And if we're ever going to be able to bring the data together, integrate it, and use it all together, we need to have these shared representations, and ontologies are a way to approach that. And if we do map data onto the ontologies, we can then suddenly build tools that are independent of where that data is coming from, independent of the city, independent of everything, because they're all using a shared representation, which the city digital twin for Toronto demonstrates. I'll stop there.